Okay, I finally got my life together. Um, let's just go over it and raise your hand to stop me if I do anything weird, because I will. Okay, don't look in my email. I said stop looking in my email. Okay, let me make a new window. Go away. Okay, so I'm just gonna do this in my terminal because I am at heart extremely lazy. Um, so I'm just gonna put this over to the side over here, and then if you squint really hard, you can still see the data points. So I'm gonna start Python in my shell really quick, and I use light mode because I'm a nerd. But so we have this formula, which is we take the data points, subtract what my function thinks it's going to be, square it, sum it, and then divide by the number of points. So let's do that in pieces. So first, let's define all of our x points within Python. So we have, let's just call it x. Actually, I'm going to port numpy first. Okay, so then let's define an array for x, and we'll do make an array. And then I'm just going to put in all of these values, and there's only 5, so it'll be okay. So 0, 5, 3, 1, 7. And then let's do the same thing for y. So let's make another array without typos. And then 0, 15, 27, 13, and 18. And then we also have this model equation, which is teeny tiny if you're anywhere but the front row, but it's y equals 10x plus 3. So let's do the same thing. We're going to define a function. I'm going to call it f because I'm bored and I don't want to do anything more interesting. F of x, it takes in one input, and then we're going to have it return that same equation. So 10 times x plus 3. Are we all like with me? Okay. So let's actually calculate what my function thinks all of these y values should be. So this is going to be y expected. So I'm going to take my function f. Let's call these y predicted. I'm sorry, all like the terms are different, but y predicted equals what my function thinks the y value should be. So f, and I'm going to pass it in x again because those are my observed x values. So what does this look like? It looks like this. And whether or not those are good predictions, again, you can look with your eyes. And again, I made all these numbers up. So these predictions are terrible, but we're going to quantify how bad they are by using this equation. So let's calculate the first part, which is our actual y values, which is y observed. So y minus my predictions, so y predicted. And then I need to square that. So this is us just translating the equation on the slides into code. So let's square this. And then we're going to sum it. So put more parentheses. And then sum this. And then we're going to divide it by the total number of points, which is 5. Okay, did I mess this up at all yet? Raise your hand at any point if I mess it up, because I mess this up every single semester. I just do something wrong. It looks okay. Okay, we got 902. Did anyone get anything different? That feels super high, but I don't remember what it's supposed to be. Okay, I'm gonna assume that I'm right. So the total error that we got was 902.8, which means that we did a really bad job, which we knew already. Let's go back here. So get rid of this. Okay, so here are the most common types of error formulas that you're going to see. The first one is the one we just did. This is called mean squared error. And the name of all these equations usually tells you exactly how to calculate it. So for this one, we have the error, which is the difference between the actual data and what your function thought it was supposed to be. And then it's squared, so you square it. And then it's the mean, so you sum over all of them, and you divide by the number of points. So that's the average. So it's the mean squared error. Super convenient. Root mean squared error is just mean squared error, so it's this thing. and then it has the R for root, so you just take the square root of the whole thing. Also very convenient. The name tells you exactly how to calculate it, so if you ever forget, just go in order of the letters and you'll be fine. Something important to note about mean squared error is that this is the same thing as variance. I know that when I was learning about variance in high school, I was like, this is the stupidest concept ever, because we always just take a square root and use a standard deviation. But actually, variance is super important, and it's the same thing as MSE. So something important to keep in mind. Brother. Okay. We have like one slide about chi-squared that I'll still to include. And I think it shows up in the homework. But chi-squared is also a measure of fit. It has like a slightly different equation. It looks very similar. There's two types of chi-squared. There's one for categorical variables, which you may have seen before. This is a different one. This is for quantitative variables. So you have, this looks very familiar by now, hopefully. The actual point minus what your model thinks it's supposed to be, divided by the error at that point. The error at that point will have to be given to you. Either it's determined through the experiment or included in the data file. You can't like determine this yourself. And then you square the whole thing and you sum over all of them. So hopefully the structure is starting to look kind of familiar. They all kind of look like this. And then you can calculate a very similar quantity, which is where you divide it by the number of points and the number of degrees of freedom, which is the number of variables that you have. So in this case, we would have X and Y, which would be 1 degree of freedom because you only have X. I mean, I'm not going to talk about this anymore because I don't ever really use it, but it's there if you ever need to refer back to it. For doing curve fitting, there's two main packages that I usually recommend. We're going to use this one because it's harder, and then this one is easier, but it can only fit polynomial functions. So quadratics, straight lines, cubics, kintics, and all that stuff. This one can do any function form you want. So this can do sigmoids, it can do polynomials, it can do like exponentials, it can do all sorts of terrible things, which is why we're going to learn how to use this one first. But this is also an option, and it's like a lot more intuitive to use. Okay, demo time. We're going to run through, actually, do I want to do this now? Or actually, let's learn more first, sorry. So let's talk about linear regression really quick, because I just want to do this during the demo while we're there. So linear regression is curve fitting. It's just like a slightly special case, even though it sounds very fancy, it's not. Linear regression is literally just about fitting only straight lines to your data. And the equations that you can use to generate these straight lines are the best fit line by default, just because of the way that they're constructed. If you want to like learn the mathematics behind that, take data 8 or something, it's not that complicated. I don't have time to talk about it. But just know that that is true. If you do linear regression, it will be the best line for your data set. But once you have your line, you want to figure out if it's good or not. Sometimes you can't just look at it and see if it's a good fit, especially once you have more than just one variable on the x-axis. Like if I gave you like a 4-dimensional matrix and I was like, put a straight line on it, that's really hard to visualize. So there's other ways of figuring it out. One of them is R and R squared. Again, you probably heard of this before, but we're going to talk about it anyways. These both measure the spread of your data set. So the sign of R is the slope of your data set. So negative sign, negative slope, positive sign, positive slope. The more interesting part of R would be the absolute value, so the magnitude of the value. So if R is super close to 1, like it's 0.99 or negative 0.99, like the absolute value is very close to just 1. And that means that your points, like your data points, are basically along a straight line. So linear model is super good, very appropriate. If it's very close to 0, then that means that there isn't a super strong linear shape within your data. So a linear model might not be super appropriate. The super important caveat to using R is that if you get a value that's close to 0, that doesn't mean that there's no relationship in your data. It just means there's no straight line. So let me show you some pictures so we can see what that might look like. This is always very important to keep in mind. So both of these plots, ignore the axes, would have an R value of 0 or very close to 0. This one, obviously there's no linear association, so you'd expect an R of 0. It's just a cloud. But this one would also have an R of 0, but there's very clearly like a shape in the data. So you can absolutely fit aligned to this data, and there is a strong relationship. It's just not linear. So that's always something you should keep in mind when using R. And you should always make sure you can try to visualize at least part of your data before you start to analyze it. Okay, let's do like a really quick practice. And I think after this, there's more slides, sorry. Okay, so for R, I gave you 3 plots that I stole from the Data 8 textbook. And these all have different values of R. So think about it for like 17 seconds, and then we're gonna rank them from like R value, R magnitude closest to 1, and then closest to 0. Okay, think about it for like a little bit.
Oh. Yeah. This is just R and R squared, so I think we're just on the over its absolute value. Yeah, so. Exactly.
Okay, let's talk about it. Okay, how do I want us to talk about it? This is gonna be 1, and then 2, and then 3. So out of 1, 2, and 3, why don't we like raise 1, 2, or 3 fingers somewhere so I can see what we think? So remember 1, 2, 3. Okay, which one has the highest absolute value of R? Okay, we got a lot of 1s. We have a 5.
Okay.
Okay. Okay, we have a lot of 1s. That's correct. This one has the points that are closest to being on a straight line. And I asked for the absolute value, which makes it like a little bit more confusing, but yeah, that's absolutely correct. And then which one out of 1, 2, and 3, or I guess 2 and 3 has the smallest absolute value of R? Okay, we're getting a lot of 2s. These are actually more similar than I remember, but it's this one. The points are the most blobular out of all of them. They're very nebulous, and there isn't a super strong linear association. So that's correct. Good job. Okay. This is like kind of a grab bag of stuff to keep in mind when you're doing linear regression and also just any kind of curve fitting. So the first like buzzword you'll see a lot is overfitting. So overfitting means that your model or equation works really well for the data set that you have. But if I were to give you a whole bunch of like new data from like the same experiment or the same process, it would not predict well at all. And usually that means that your model equation has way too many parameters. Now, the really classic example of this would be if I gave you like any number of data points, you can theoretically fit an n-1 degree polynomial to that many points. Just hit my backpack. But if I gave you like another point, your model like would not know what to do with it because it perfectly fits all of your data points. But if I gave you this one, it would be like super off. So it doesn't generalize well. In general, you want to have way more data points than parameters in your equation. The other thing to look out for is oversimplicity, which is like the opposite thing, which means that you have way too few parameters. So this would be like if I gave you a parabola and you fit a straight line to it, you're missing a lot of complexity in the data. And then for linear regression in particular, we're going to do this in like maybe 15 minutes, depending on how fast the demo goes. But you want to check that your linear model for linear regression fits your data appropriately. And one thing you can do for that is look at they're called residual plots. And residual plots basically zoom in on patterns in the data relative to your model. And if your residual plot has any kind of shape in it that isn't a cloud, then you probably don't want to use a linear model. And again, we'll show this, so it makes a little bit more sense. Good residual plots will look like a cloud. There's no shape at all. So choose the model equation carefully. There's like no super good formula to picking a good equation with like a perfect number of parameters. You just kind of have to guess. So sorry, but that's kind of how it works. This is an example of some residual plots. So here's the original data. Looks pretty straight. Residual plot has a very clear shape in it. This has like a U. So this means that your data is actually not as linear as it looks. And if we look at it really closely, you can see that it kind of does have a slight curve to it that gets like blown up in the residual plot. So it helps us identify that this isn't a super good idea. And then for this one, here's the real data. Here's the residual plot. This is a cloud. We did a good job. This is linear. Okay, this is all the places I stole stuff from. Anyways, let's do the demo now. So go ahead and open. You can either get like a Jupyter notebook open, or you can open something in like VS Code, which I think is what I did. Just something with cells in it so you can write code. That's way too big. Okay. And I'll give you guys like 30 seconds to get something open and then we'll get going. Okay, so once you have your thing open to write code in, go to B courses, files, demos, and then download. There's a file in there called like S25 CF data. So download that and then put it in the same folder that your code file is in, because we're gonna need that. I'll go find it in B courses with you. So it's in here, and then it's the S25 CF demo data. So download this one. I put it in like 10 minutes before class started. Don't worry about it. And then put it in the same folder as your notebook. Okay, raise your hand if you're ready, like you have a notebook and you have the data downloaded somewhere. Okay, we have like half. Ready? Okay. Okay, I'm gonna move on then. And then stop me if I like get too far ahead or something. Ugh. Okay, so let's import a few things first, as we always do. We're gonna import NumPy. We're gonna import pandas. Matplotlib, of course, is a staple. And then we're gonna import one more thing, which is our scipy.optimize package that I showed you for like 10 seconds on the screen. I'm gonna pretend like I did that right. I did not do that right. And then once you're done importing all these things, run the cell before doing anything else and make sure it works. And then we'll move on. Okay, so now that we have all this stuff and we have the data downloaded, let's read it in. So we know that we can do that using pandas. So let's call it df, and we're gonna do pandas.readcsv. And then I called it S25 CF data.csv or something like that. Nope, I didn't call it that. What did I call it? demo data. Okay. It should look like that once you have it read in. Okay, raise your hand if you're here with me. Okay, we have like 3 people. Keep cooking. Yeah. So dot head is like a pandas function and it shows the first 5 rows. Okay, raise your hand if you got everything shown. Okay, that's a lot better. Let's keep going. So now that we have our data, let's take a look at what it looks like. So let's plot it. So a figure sandwich that I hope I drilled into all your brains like 3 weeks ago. Let's make a scatter plot. And we have our x values and our y values. I don't know why I said it like that. So figure, scatter plot with x and y, and then show. And then it should look like a little bit like this. Mine doesn't fit, but you should have something like that. All right, I'm just gonna move on. So we have our data, we know like what it looks like. I'm gonna use my eyes and look at this and say that it looks like it's a straight line. You might have differing opinions. I think it looks straight. And I'm teaching, so it's whatever I want to do. And I want to do a straight line. So how we do that using scipy.optimize.curvefit is we need to give it a few things. So the first thing we have to give it is what our model equation should look like. And since I want a straight line, I need to give it the general format of a straight line. So the way that we do that is we define a function, sort of like how we did for the error problem earlier. And I'm going to call it also f. Don't worry about it. And the arguments that this model equation needs to take in are all of the things in a model equation of this type that can change. So I want to do a straight line, and the equation for that is y equals mx plus b. So the numbers, the inputs are x, but if I want to create any straight line in the universe, I can change m and I can change b. And by changing both of those parameters, I can generate any straight line I want in the world. So those are going to be the arguments into my function along with x. So x always goes first. So I always start with a function and then, okay, x as an argument, the first one, or it won't work. And then we're going to give it the parameters in the equation such that if I change those things, I can make any equation of this type that I want. So there's going to be m and b. And then the thing that you return is almost trivial. We're going to return m times x plus b. Because that's just the equation for a straight line. If I wanted to like fit a different equation to this data, I would just change this function to give it a different shape. But for now, we want to make it as generic as possible and say we can take any slope in, any y-intercept, and then make a line with those things. The next thing, after we give it the model equation, we have to define like our best guess for like sort of around what we think this is going to look like. And that might sound really counterintuitive because if I knew what it was supposed to look like, why would I do this? But your guesses don't have to be super good. You just need to give it like an idea of where to start looking. So we're gonna pretend like I don't know anything about lines, and I'm gonna give it 1 and 1. For any polynomial structure function, your initial guesses, which I'm calling p0, like really do not matter that much. For more complicated functions, you should maybe try like a little bit harder. but for polynomials, whatever you want is fine. So we're gonna give it 1 and 1, or whatever you want. And then let's actually call the curve fitting function. So this is called, since we imported the package as fit, I think, we're gonna call fit the package and then the function curve fit. And then ignore the pop-up, I can't get rid of it. There's the arguments we're gonna give it in this order are going to be the function we defined, so our model equation, which I called f, like a very creative person. And then we're gonna give it our data values. So we have to give it x and y separately. So we have our x values, and then we have our y values, and then we have our initial guess at the parameter values for m and b. So it should look like that in that order. Let me make this a little bit bigger. It should look like that. And then for what this function returns, it returns two things. I don't know if you've seen that a lot in this class so far, but you know how normally like when we call a function, it returns a value, we just say like z equals, and then it looks like this, like z equals some function call. So this returns two things. So it's gonna look more like this. And it'll return one input to each one of those variables. So in this case, what this function returns is it's going to return its estimated parameters. So it's going to give us the best fit that it could find for the slope m and for the y-intercept b as one array, which is the first argument it returns. We're going to call that param, show for parameters. And then the second thing that it returns is something called the covariance matrix. And that also is a separate output, which we're going to capture in this return argument called cov. So this means that we have our curve fitting function, and then it's going to give us back two things. It's going to give us the parameters, its estimated parameters, and then the covariance matrix. And I'll talk about that super quick later. So then balls to the wall, just try to run that and see if it works. Mine worked because I'm really cool. If yours doesn't work, let me know, I'll take a look. So let's just do one. So this won't error, but what it does is the variable z will instead contain two separate values. So this will be a tuple. And if you take a look at it, it has like two different arrays. Whereas if we give it two things at the beginning, like the first parameters will have the first array, and then code will have the second array. So it's just a little more convenient, but you can do it like this too. Okay, raise your hand if this like ran for you. It worked. Nice, very nice. Okay, we got a bunch. Okay, so let's take a look at what we actually got out of this. So we have params, which we saw this briefly, but we can tell that this is an array and it has two numbers, and we know which parameters these correspond to because they're going to be in the same order that our model equation takes them in. So if you remember, our model equation f took m and then b, so this is going to return m and then b. So they're in the same order. And then if we take a look at the covariance matrix, it gives us a 2x2, which might be a little unexpected. But what the covariance matrix does is to like simplify it a lot, it basically measures how all of our parameters vary in respect to each other. It might not make sense, but basically, if we measure how a parameter varies with itself, that's the same thing as its variance. And so the variance ends up along the diagonal because we're measuring a parameter to itself, and this is like a grid. So this is like m, b, m, and then b. So it's a symmetric matrix. This is the variance of m, This one is the variance of B, because we're measuring how that parameter varies with itself. And the reason why this is helpful is because if we know the variance of our estimated parameters, we can, in some limited circumstances, take the square root of that to get the standard deviation and then use that as a proxy for the error of our estimate. So that can be super helpful, and that's why it gives this back to us. Anyways, that was really boring. So let's take a look at how our line actually did. And just keep in mind that the errors are along the diagonals of the matrix. Yeah. Yeah, P0 was just like our initial guess for what we thought the parameter should be. And it mostly tells it where to start looking. But like what it returned back is like not anywhere close to what we specified, and that's fine. So we're gonna actually check what it gave back to us because it was so different. And then we'll see that it actually did a good job. So let's go ahead and separate out our estimated parameters from these outputs. So we have like M, I just call it M. And then we know that it's the first element in our parameters array that was returned to us. And then B is going to be the second one. So let's just pull those out to make it a little bit easier. And then I'm going to skip over the errors for now just because I don't feel like doing it right now. I trust you all remembered what I just said. And then let's go ahead and calculate like what we did for the error problem, which is for all of our x values, what does our model equation think that value should be? So we have our function f, which we know will give us a linear equation. And we're going to give it our x values. Sorry, we're going to give it our x values. And then we're going to give it our estimated slope and our estimated y-intercept. And then this is going to give us back a bunch of y values, each one of the x data points that we got, according to our estimated equation. And I'm going to call this y-est, or estimated. And then once we've done that, we're going to go ahead and plot it all in the same graph so we can compare them next to each other and see if it worked. So make a figure. And then we're going to do a line plot of our x data values again, and our estimated y values. And then let's also put our scatter plot of our x values. Again, sorry about the pop-up. And our y values. Okay. So, okay, don't worry if you didn't get all that yet. I'm just going to show you what it's supposed to look like because we're running out of time. It should look like this. I'm sorry, the text is tiny. I'm going to post this on B courses. But here's our original data. Here's our line. Looks pretty good. I'm happy with this. Nice. We did a good job. Any questions before I move on to like the last part? Or like scroll up to anything? We're good? Yeah.
Can we do all this in one cell?
Yeah, the world is your oyster with cells. You don't have to split it up. I just like doing it. Okay, so now that we have our line, if we remember what I talked about with residuals, because we're technically doing linear regression right now, because I fit a straight line to this, we should probably check if this is as good a fit as I think it is. Right now it looks pretty good, but you can never be too sure. So let's go ahead and check out the residuals. So if we remember, which we probably don't because I would have forgotten, a residual is the difference between the predicted value and the actual value. So in this case, it's going to be, I think I called them like our like predicted values, I can spell, minus our actual values. So in this case, we would have, I don't know, I'm reading this twice. Our y estimate minus our actual y's. And that's going to give us basically the error between our line and each one of our data points. And this works because for every one of our data points, we already generated a prediction. So then we'll go ahead and plot this to make our residual plot like I showed you guys earlier. So make a figure, And then we're gonna make a scatter plot of our residuals with respect to our estimated Y values. And if I scroll down to take a look at this, we can see that I totally boned it up because this is a shape, which is not what I want. I don't want this to look like anything at all. This should be a cloud. I did a good job, but it's not. It looks like a parabola. So that tells me that my original data, all the way up here, is actually not a straight line. And it's not, when I generated this data, I actually made it a parabola. So our analysis is correct. A linear model is not appropriate because the data is not linear. Or the process that generated the data was not a linear process. Any questions about that? Yeah,
Okay, what's scatter? Is this supposed to be X on the, or is it?
yeah. But I'm using my estimated Y values as the x-axis.
Okay.
That's just like the format for residual plots. It's basically like, you can think of it as taking the, like if the plotted line is like this, you kind of take the plot line and then just go like that.
Okay.
Any other questions? This is like the last concept, so after that, like we're done. Good? Okay. Well, that's it for today. So feel free to go home or whatever you guys do on Thursdays. But yeah, I think we have homework coming up that's due. There's some due earlier this week, and then there's some more due coming up. I think the next two homeworks are both due on the 29th, so keep that in mind and just get those in. And enjoy the rest of your day and your weekend. Thanks for coming.
Work up. On the